Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the real analysis class. In today's lecture, we are going to discuss a very important topic, that is the irrationality of square root. Actually, in this topic, we will discuss when positive integers produces are an irrational number. Today lecture might be a long lecture, so I suggest to you that you can watch this lecture in different settings. So in this lecture, we will discuss the irrationality of the following numbers: square root 2, square root 3, square root 5, square root 7, square root 6, square root 8, square root 10, square root 12, square root 15, square root 18, square root 72, square root 75. And the last one is square root 32,805. So in this lecture, we will discuss the irrationality of all of these square roots. All of these square roots are actually irrational numbers. This is our target to prove. And further, in this lecture, we will discuss an important result, that is show that product of a non-zero rational number and an irrational number is an irrational number. That the product of a non-zero rational and an irrational number is always an irrational number. So before going to discuss, we will discuss some important result from number theory that will help us during the lecture. The first result from number theory that we will use: if P is any prime and A and B are two positive integer, P divides this vertical line, represent divide, and read as P divides AB. This line is used for division. So we call this P divides AB. So A and B are two positive integer and P is your prime number. If P divides product of A and B, then P divides either A or P divides either B or both. For example, if our P is suppose 5 and product of two number is 35, that is actually 5 into 7. This is suppose A and this is your B. Now you can see that your P, that is 5, divides this product. This implies 5 divides 5. Similarly, if your product AB is like as 125, and 125 can be written as 25 into 5. In this case, your prime P divide both numbers, that is 25 and 5. So if P is a prime and divides both product A and B, then P divides A or B or both. The second result: if P is prime and divides square of a positive integer A square, then it must be that P divides the number without square. If P divides A square, then P divides A also. The third number: if A divides B square. Now in this case, A is a composite number. If A divides B square and A is a composite number, then we cannot say, or it does not imply that A divides B. If the divisor is a prime and divides the square of a number, then in case of prime, divisor will always divide the number without square. But if in case divisor is a composite number and divide the square of some number, then without square, it does not imply that it divide that number. For example, as 12 divide 36, this is okay. But as 36 is the square of the number 6, so without square, 12 does not divide 6. 12 does not divide 6. So in case of prime composite number, if it divide the square of a number, then you cannot say always that that composite number divide without the square. So what will we do in this case? Firstly, we will make the prime factorization of the composite number a. Suppose the prime factorization of a is p1 raised to power r1, that is the first prime, repeat r1 time, p2 raised to power r2 up to so on, pn raised to power rn. Mean to say the prime, in the prime factorization of a there are n primes with repetitions. Then always it must be that the product of these distinct prime always divide b square. And if p1 p2 pn are distinct primes that divides b square, then it must be that they divides the b without square. Further, the last result that we will use, if abc are three integers and a divides the product of b and c, product of bc, if gcd, greatest common divisor, if greatest common divisor of a and b, this bracket a comma b, this is not an open interval, this is actually shows the gcd, highest common factor, greatest common divisor of a with b is 1, that is a and b are relatively prime numbers, then a must divide the third number c. This result says that if a divide a product of two numbers b and c, and the GCD of a with anyone with any of b or c is 1, then a divides must the third number. For example, here if our a is suppose 5 and the product is b is 5 and c is 7, that is the product bc is 35. Now you can see that a divides bc, our a is 5, that divides the product bc 35. Further, 35 can be written as 5 into 7, as gcd of 5 and 7 is 1, that is 5 and 7 are relatively prime numbers, so it must be that 5 divides the second number, that is 5. Now we will discuss four cases. We will discuss the four cases that will cover the irrationality of any square root. If you observe, any positive integer is one of the four type. Any positive integer is one of the four type. Observe. We will discuss four cases to show that square root n is an irrational number. Case number 1, when n is prime, your positive integer is a prime number. Second case, when n is a perfect square and product of distinct primes. Second case. The third case is when n is power of a prime and the power is odd. Third case is when n is a power of prime and where power is odd. The fourth one is when n is a composite number and contains a factor that is perfect square. We will discuss all of these four cases. Your any positive integers, you know your positive integers are 1, 2, 3, 4 up to so on. Any positive integer is either 4 of the type. It may be a prime number, it may be a product of distinct primes, it may be a power of single prime, but here power is odd. And further, your positive integer may be a composite number that contain a perfect square. After discussing these all four cases, inshallah you will be able to check the irrationality of any square root or any positive integer. So in the following example we will discuss following all cases. In the case number 1, when n is a prime number, in this case we will show the irrationality of this square root. That is, we will show that square root 2, square root 3, square root 5, square root 7, square root 11, square root 13 are all irrational numbers. So firstly we will discuss how we will show that square root 2 is an irrational number. So our first target is to show that square root 2 is an irrational number. You can see that 2 is a prime number, so square root 2 will always an irrational number. To prove this, we will use the contradiction. Let on the contrary that square root 2 is a rational number. Let on the contrary square root 2 is a rational number. You know that if square root 2 is a rational number, you can write it as p over q form. So it can be written as a p over q form. So we write square root 2 is equal to p over q, where p and q are integers, q is non-zero, and further p and q, the GCD of p and q is 1. That is, they have a no common factor, or they are in the simplified form. Here we suppose that square root 2 is a rational number, so it can be written in p over q form. P and q both are integer. Here p is not a prime number. P and q both are integer. You can write it as m over n form. P and q both are integer. The denominator q is non-zero. Further, they are in its simplified form, so their GCD is 1. Mean to say that the common factor between both p and q is only 1. Throughout the lecture, I will use the strategy. That I will write any square root equal to p over q form. I will suppose p and q have a no common factor. At the end, I will show that they have a no common factor other than 1. At the end, I will show that p and q has some common factor other than 1. So this is our strategy that will lead to the contradiction. At the start, we will suppose they have a no common factor other than 1. At the end, we will show that p and q both are a multiple of some number, mean to say they have some common factor other than 1. This is our strategy throughout the lecture. So, as we suppose under root 2 is equal to p over q, so this can be written as p is equal to square root 2q. By squaring on both sides, we have p square is equal to 2q square. This is our equation number 1 that we will use. This is our equation number 1. Now, from the question number 1, we can see that the right side, that is 2q square. This right side 2q square is a multiple of 2, so 2 will divide 2q square. As 2q square is equal to p square, this means 2 divide p square. We have discussed a result. If a prime number divide the square of the number, then prime number will divide the number without square. So here 2, that is the divisor, that is a prime number here. This divide the square of p. This implies that 2 will divide p without square, that is 2 divide p also. If a prime number divide the square of a number, then that prime number will always divide the number without square. So 2 will divide p also. This shows that p is a multiple of 2 because you know, if a number is divisible by 2, then it will always an even number. So p is here even number. So p is a multiple of 2. So 2 p is a multiple of 2. Now you can write p it as, let p is equal to 2m, where m is an integer. Uh, Now put this value of p is equal to 2m in equation number 1, or squaring on both sides to find the value of p square. We have p square is equal to 4m square. By using equation number 1, the equation number 1 is p square is equal to 2k square. So putting this value of p square, that is 4m square, in equation number 1, we have 4m square is equal to 2q square. So this is our second equation. From this equation, we have, by cancelling 2 on both sides, q square is equal to 2m square. As the right side, that is 2m square, is divisible by 2, this shows that q square is divisible by 2. In other words, q is a multiple of 2 here. This shows that q square is divisible by 2. Again, using the result that if the square of a number is divisible by a prime p, then that number without square will also be divisible by that prime p. So here 2 is our prime, q, this is q square. So 2 divides q square. This implies 2 will also divide q. Now from question number 1 and 2, q is a multiple of 2. From question number 1 and 2, we can see that p and q both are even integers. So both have 2 as a common divisor, which is contradiction to our assumption. Our assumption was p and q both have only 1 as a common factor. Our assumption that 1 is the only common divisor of p and q, hence our assumption is wrong. So square root 2 is an irrational number. So this is the irrationality of square root 2. Next we discuss an example of square root 3 with a similar pattern that we have used in irrationality of square root 2. We will discuss that square root 3 is also an irrational number. So firstly, we suppose on the contrary that square root 3 is a rational number, so it can be written in p over q form, where p and q both are integers. They have where q is non-zero, they have only 1 as a common divisor, that is p and q are in the least form. So we will reach at this step, square root 3 is equal to p over q form. From this step, p is equal to, we have p is equal to square root 3. Square root 3 mean to say this is now square root 3 is equal to p over q. By squaring on both sides, we have p square is equal to 3q square. So this is our question number 1. From this equation number 1, you can see that the right side, that is 3q square is divisible by 3. This number 3q square is a multiple of 3. So obviously this is divisible by 3. 3q square is equal to p square. So this shows that 3 divide p square. Now again, using the result, if a prime p divides the square of a number, then that prime p will also divide the number without square. So if 3 divide p square, this implies 3 divides p. P is not here prime. P is here integer in this example. So p is a multiple of 3. So p can be written in this form. P is equal to 3m and m is an integer. So substituting this value of p is equal to 3m in this equation number 1, we have, or squaring to find the value of p square, we have 9m square, and by using equation number 1, we have our p square is equal to 3m square. So this will become 3m square equal to 3q square. This is 9m square equal to 3q square. By cancelling with 3 on both sides, we have q square is equal to 3m square. Now this equation number 2 shows that the right side, that is 3m square, is divisible by 3. So the left side will also divisible by 3. So this shows that 3 divides q square also. So 3 divides q square. This implies 3 is a prime p that divides the square of a number. So 3 divide q square without square. This implies 3 divide q. From question number 1 and 2, we can see that p and q both have 3 as a common divisor, which is contradiction to our assumption that 1 is the only common divisor of p and q. Hence our assumption is wrong. So square root 3a is an irrational number. This is not. In the similar way, you can prove that square root 5, square root 7, square root 11, etc. are all prime numbers. Next we move towards the second case. In this case, the number inside the square root, that is n is not a prime number. In this case, our n is not a perfect square. In this case, our n is not a perfect square and product of distinct primes. N is not a perfect square but product of distinct primes. So for this case, we will discuss the following examples. Square root 6, square root 10, square root 14, square root 15, up to so on, etc. Are all the irrational numbers, because in all of these square root you can see that these are the product of a distinct rational. None of the number inside the square root is a perfect square. For example, square root 6 is the product of distinct prime 2 and 3. Square root 5, this is product of 2 and 5. This is 2 and 7, and this is product of 2 and 3 into 5. So firstly, I will discuss here irrationality of square root 15. Square root 15. Just a minute, please. Okay. Next, we will show that square root 15 is an irrational number. Suppose square root 15 is a rational number on the contrary, then it can be written in p over q form. So square root 15 can be written as p over q, where p and q are integers, q is non-zero, their GCD is 1. So this implies we have equation p is equal to square root 15 q. We have p is equal to square root 15 q. From this equation, by squaring on both sides, we have equation p square is equal to 15q square. This is our first equation that we will use. Further, this equation can be written as 3 into 5 q square. This is the important step. Say this equation as equation number 1. Acha. We can see that p square is a multiple of 15. That is, p is product of two primes, 3 and 5s. So p itself must be multiple of 3 or 5 or 15. As above, we have discussed our result. If a composite number a divide b square, then it does not imply that a divide b. But if we make the prime factorization of a, suppose p1, p2 are the prime factorization of a that divides b square, this implies p1 and p2 both divide b. So here further, this is also important. Here 15 is a product of 15 is although a composite number, but this is actually product of distinct prime. Mean to say there is a no prime with some power. Like as in case 12. 12 is actually product of 3 into 4. That is 3 into 2 square. So this is another case that we will discuss in the next case. 15 is a composite number, but it is product of two distinct primes. So it must be that this equation right side 15q square is divisible by 3, that is 3 divided square p square. Here 5 also divide p square, and lastly 15 also divide p square. So there are here three cases. In all these cases, if 3 divide p square, this implies 3 will divide p. If 5 divide p square, this will also divide p. If 15 divide p square, this will also divide p. So these are the three possibilities for p that you can use here. I again repeat, here the right side, that is 15q square, is divisible by 15. So the left side will also divisible by 15, because p square is equal to 15 divide 15q square. 15q square is equal to p square. This implies 15 divide p square. Now as 15 is a product of 3 and 5 and both are prime numbers, so from this 3 will divide p square, 5 will divide p square, and 15 will divide p square. This implies 3 will divide p, 5 will divide p, and 15 will also divide p. 15 is a composite number, but it is a product of distinct prime. When a composite number is product of distinct prime without any power of prime, then that composite number, this result hold that for that composite number, that is only the product of distinct prime, not containing any power of prime. If it divide the prime p square, then it will divide without square. If that divide, sorry, this p here, p is an integer, not a prime p. I will discuss here case number 1. If we take p is a multiple of 3, with respect to your exam point of view, you will consider only one of the case for p. You can either consider p is a multiple of 3, p is a multiple of 5, or p is a multiple of 15. Here I am going to discuss all of the three possibilities that can be used for p. Case number 1, if p is a multiple of 3 from here, then you can suppose p is equal to 3m. So substituting this value of p, or squaring, firstly p square will equal to 9m square. Now substituting this p square in this equation, so by putting here p square equal to 9m square, so this equation will become 15q square is equal to 9m square. By cancelling with 3 on both sides, we have 5q square is equal to 3m square. I need to find the value of q here, not the I am not interested in to find the value of m. So from question number 2, what is equation number 2 here? I have a question number 2, 5q square is equal to 3m square, that I have obtained by putting p is equal to 3m in equation number 1. 3m whole square equal to 15q square. This implies 9m square is equal to 15q square. By cancelling with 3, we have 5q square is equal to 3m square. Now I am interested to find the value of q. As 5q square is equal to 3m square, the right side is a multiple of 3, that is the right side 3 is divisible by 3. 3 divide 3m square. 3m square is equal to 5q square. It means 3 divide 5q square. We have discussed our result. Result says that if A divide the product BC, where A, B, C are positive integer, if A divide BC, and the GCD of A with any of uh, these two is 1. That is A, suppose GCD of A and B is 1. That is A and B are prime relative, relatively prime. Then this implies A will divide the third number C. So by using this result, when 3 divide 5q square, as the GCD of 3 and 5 is 1, as because GCD of 3 and 5 is 1, that is 3 and 5 are relatively prime. This shows that according to this result, 3 will divide q square. Now 3 is a prime number that divide the square of a number, so 3 will divide the number without square, 3 will divide q. This implies q is multiple of 3. From question number 1 and 2, we can see that P and Q both have 3 as a common divisor, which is contradiction to our assumption that 1 is the only common divisor. Hence, our assumption is wrong. Square root 15 is irrational number. So this is the first case to reach that square root 2 is an irrational number. In second case, when 5 divide p square from this equation, if 5 divide p square, then 5 will also divide p. So it means 5 is a multiple of p is a multiple of 5. So p can be written as 5m. So from this equation, p square will be 25m square. So substituting this value of p is equal to 5m in equation number 1, that is this here. Substituting p is equal to 5m in this equation, we have 5m square equal to 15q square. This is 25m square equal to 15q square. By cancelling with 5, we have 5m square is equal to 3q square. Again, I am interested to find the value of q. As the right side is divisible by 5, 5 divide 5m square. Because 5m square is equal to 3q square, so I can replace 5m square with equal to 3q square. This shows that 5 divide 3q square. If 5 divide 3q square, I will again use the result as the GCD of 5 with 3 is 1. GCD of 5 3 is 1. This implies 5 will divide the second number q square. This implies 5 divide q square. 5 divided q square, this implies 5 divided q. This shows that q is a multiple of 5. So from equation number 1 and 2, both p and q both has a common divisor 5. That leads to the contradiction to our assumption that they have only 1 as a common divisor. Hence, square root 15 is an irrational number. Next, the last case for value of p. When p square is divisible by 15, in other words, when p is a multiple of 15, when p is multiple of 15, so let p is equal to 15m, and m is our integer. M is an integer. Put this value of 15 p, that is 15m, in equation number 1 here. So substituting value of p, that is 15m here, this will give us 15m square, 225m square. By cancelling with 15, this will become 15m square. This shows that q square is equal to 15m square, implies q square is a multiple of 15. This implies 15 divided q square. Because 15 is a composite number, but it is a product of only two distinct prime. So we have a result 15 will divide also q. If a is a composite number, but it is a product of only distinct primes, without any power of prime, then that number will also with if divide if that then that number will divide the number without square. So 15, that is a product of two distinct prime 3 and 5. If divide q square, it will also divide q. So in this case, q is also multiple of 15, and here p is also multiple of 15. So this shows that both p and q have a common divisor 15. That leads to the contradiction that p and q has only one as a common divisor. So our assumption is wrong. Hence square root 15 is irrational number. So in this way you can show that irrationality of those numbers, that is the product of two distinct primes. In the similar way you can show the irrationality of square root 6, square root 10. Here it is remembered that in your exam you will choose only one value of p. Either you will choose p is multiple of 3, p multiple of 5, or p multiple of 15. But in the lecture because I want to deliver my lecture in brief discussion, so I have to clear your understanding. I have discussed all of the three possible cases. Now we move towards the third case. Case number 3, when n is power of a prime, single prime, but power is odd. For example, here we will show that square root 8, you know, this is 2 raised to power 3, 27, this is 3 raised to power 3, 32, this is 2 raised to power 5, 125, this is 5 raised to power 3. So all of these numbers are power of a single prime, but power is odd. In case if power is even, then that square root will not produce a rational number, that will always a rational number. Suppose if you take 2 raised to power 4, square root of 2 raised to power 4, 2 raised to power 4 is 16, 16 square is equal to square root of 16 is 4. That is obviously a rational number. So here we will discuss only the odd power. But before to discuss this, the irrationality of the square root, we will discuss an important result. That is, we will show that the product of a non-zero rational number and an irrational number is an irrational number, because this result we will use in the following cases. Product of non-zero rational and an irrational number is always an irrational number. This is our target to show. Let x be an irrational number and r not equal to 0, that is non-zero, be a rational number. R is our non-zero rational number and x is our irrational. R is rational and x is irrational number. We need to show that Rx is irrational. This is our target. Here we will use also contradiction. Suppose on the contrary, we need to show that the product Rx is a irrational number. On the contrary, we suppose that the product Rx is a rational number. Then it can be written as in P over Q form. So let Rx is equal to P over Q, where P and Q both are integers. They Q is non-zero, their GCD is 1. Next, as here R, that is a non-zero rational number, R is a non-zero rational number. So let r is equal to m over n, because r is given, it is given that r is a non-zero rational, so it can be written in p over m over n form, where m and n both are integers, and non-zero GCD of m and n is 1. So question number 1 implies, what is question number 1? Question number 1 was Rx is equal to P over Q. That we suppose on the contrary, the product is rational number. Now substituting the value of R, that is M over N here. This is M over N, X is equal to P over Q. Multiply on both sides by N over M. The reciprocal of M over N we have X is equal to NP over MQ. Now here there are 4 integers M, N, P, Q. As P, Q, M, N are integers, and the denominator Q and the denominator N are non-zero, we know that the product of two integers is always integer. So the NP, that is the product of two integers, this will always an integer. Similarly MQ, this is also product of two integers, so the product of two integers will always an integer. So let the product NP is equal to Q1 and the product MQ is equal to Q2. So our x that was NP over MQ. NP is equal to Q1 and MQ is equal to Q2. Our x will become Q1 over Q2, which shows that x is a rational number, because this is at this time this is a quotient of two integers where Q2 is non-zero. But at the start we have supposed that x was a irrational number, sorry. So our assumption is wrong, that product of Rx is a rational, hence the product of a non-zero rational and an irrational number is always an irrational number. Now we will show square root 8, square root 27, square root 32, square root 125, etc. are all irrational number by two methods. So firstly we discuss irrationality of square root 8 by using two ways. By using two ways we will show square root 8 is an irrational number. Method number 1. As you can write square root 8 is equal to 2 square root 2. Here 2 is a rational number and square root 2 is an irrational number. So by using theorem or result that we have proved, square root 8 is a product of a rational and an irrational number. So from theorem 1.1, square root 8 is an irrational number, because theorem says that the product of a rational, non-zero rational and irrational number is always irrational. Method number 2, in this method we will not use the reference of any theorem. We directly prove that square root 8 is an irrational number. So let square root 8 is a rational number on the contrary. So square root 8 can be written in P over Q form. Square root 8 is equal to P over Q form, where P, Q are integers, Q is non-zero, GCD of PQ is equal to 1. So from by squaring on both sides we have the equation P square is equal to 8Q square. As the right side is divisible by 2, 2 divides 8Q square. This implies that 2 will divide P square. Uh, 2 divides 8Q square. 8Q square is equal to P square. So by replacing 8Q square is equal to P square, we have 2 divides P square. Now again using the result, if a prime number divides the square of a number, then that number will divide the number without square. So this implies 2 divides P. This shows that p is an even integer, so let. In this case, uh, some there is a strategy that we will use here. This is something different from above. Here p is even integer, that is multiple of 2. So if you suppose p is equal to 2m and replace this value of p is equal to 2m in this equation, we have 2m square is equal to 8q square. This will give us 4m square is equal to 8q square. By cancelling, m square is equal to 4q square. Because we are interested to find the value of q square, we are interested to draw the conclusion of q square, that what type of q is a multiple of 2, 3, 4, 5, etc. Now from this equation you cannot draw any conclusion of q square. You can draw conclusion of m square. You can see that m square is a multiple of 4, so 4 divide m square. But we are not interested to find the value of m. We are interested in the value of q. This will be possible when, this is important point to note. This will be possible, you will find the value, you can draw the conclusion about q when there will be some coefficient other than 1 with m square. Because here the coefficient of m square is 1, you cannot draw any conclusion about q square or q. So that's why I will not suppose here p is equal to 2m. This will not work here. Because p is an even integer, so we can suppose p is equal to 4m, because all multiple of 4 are also even integers. Even integers are not always multiple of 2. This is not necessary. 4m will also produce even integers. So in this case, the value of p that will work here, p is equal to 4m. So let p is equal to 4m here. So by substituting this value of p is equal to 4m in this equation, we have p is equal to 4m from this equation. By putting this value p is equal to 4m, we have 4m square is equal to 8q square. This implies 8q square is equal to 16m square. By cancelling, we have q square is equal to 2m square. Now you can see that you can draw conclusion about q square, because at this time the coefficient of m square is not 1. This is important point. In the previous case, the coefficient of m square was 1. You are unable to draw any conclusion about q square. Now you can say that q square is a multiple of 2. From 2, it is clear that q square is an even integer. This implies q is an even integer. From 1 and 2, we can see that p and q both are even integers. So both have 2 as a common divisor, which is contradiction to our assumption that 1 is the only common divisor of p and q. Hence our assumption is wrong. So square root 2 is an irrational number. In the similar manner, in the similar two ways, you can prove the irrationality of square root 32, square root 27, etc. Now we will discuss the last case number 4. That is when n is a this is not correct. Case number 4, when n is a composite number and contain a factor that is perfect square. Our n inside the square root will be a composite number and contain a square factor. In case number 2, we have also discussed case of composite number, but there our n was the product of distinct primes. In this case, our n is a composite number and contain a square factor when we make the prime factorization of n. Like as In this case, we will show that square root 12, square root 18, square root 72, square root 75, and one of the number square root 32, 805 are irrational numbers. If you make the prime factorization of all of these numbers, you will see that all of these numbers contain scale factor. For example, let us start from square root 12, method number 1. As square root 12 have the prime factorization 2 square into 3. Now this number 12 contain a scale factor that is actually 4. 4 can be written as 2 square. So we can write square root 12 is equal to 2 under root 3. As here 2 is a rational number and square root 3 is an irrational number. Product of rational and non-zero rational and irrational number is always a rational. So we can conclude that square root 12 is an irrational number. Next we prove irrationality of square root 75 by using method number 1. I will discuss the method number 2 also here. Square root 75 can be written as 25 into 3. So 25 is a perfect square. That can be written as 5 into square root 3. So again, by using the result, 5 is a rational and square root 3 is a rational number. The product of these two numbers will be a rational number simply. Square root 75 is a irrational number. Last one. Square root 32,805. If you make its prime factorization, this will be 3 raised to power 8 plus into 5. 3 raised to power 8. This will be a perfect square. That is actually 81. So this will become 3 raised to power 4. That is 81 into square root 5. 81 is a rational number and square root 5 is an irrational number. Product of rational and irrational number is again an irrational number. Hence the number is irrational. Now I will discuss method number 2. I will prove the irrationality of square root 18 by method number 2. Method number 2 means without giving any reference of the theorem, I will directly show that square root 18 is a irrational number. So the starting line are the same. That square root 18 is a rational number. It can be written in P or Q form. From this we have P is equal to square root 18Q. By squaring on both sides we have equation. P square is equal to 18Q square. That can be written 3 square into 2Q square. Now there is an important point at this step. 18 is a composite number, but it is not a product of distinct prime. The distinct prime factors have some power, like as 18 is 3 square into 3 square into 2. So this is the this factor 3 have the power 2. So in this case you cannot say that if 18 divide p square, this does not imply that 18 divide p in this case, because for example 18 divide 36, this is correct, but 18 does not divide square root of 36, mean to say 36 is actually square of 6. So if 18 divide 36, 18 will not divide this number without square, that is 6. So if a number is a composite number and if it is only product of distinct prime and none of the prime contain any power, then that case composite number, if divide the square, then that will divide that number without square. But if we have a composite number that contain some power in the prime factorization, then if that number divides the square of some number, it does not imply that that number divides the number without square. Now, in this case, what will we do? From question number 1, we can see that 18 divide p square, but it does not imply that 18 divide p. As prime factorization of 18 is 3 square into 2, so every multiple of 18 is divisible by 6. So from this step, actually I have to choose possibilities for the number that can divide p square here. At this step, we have to set p equal to some multiple. At the right side of p square contain two distinct primes, that is 3 and 2. So you can set p is equal to 3m, either you can set p is equal to 2m either, or you can set p is equal to 6m. You cannot set p is equal to 18m here. This is wrong. So in this case, when your composite number contains some power, you will choose p like as this. In case suppose our p square is equal to 12 q square. If we have to prove irrationality of square root 12, now 12 can be written as 2 square into 3. So in this case, again you can let p is equal to 2m, q is equal to 3m, p is equal to 3m, and p is equal to 6m. But p cannot be considered equal to 12m. So I am considering here this case p is equal to 6m. So if 6 divide the number 18q square as 6 divide 18q square is equal to p square. This implies we can replace 18q square is equal to p square. 6 divide p square, this implies 6 divide p. Although 6 is a rational number, although 6 is a composite number, but this composite number 6 is only product of two distinct primes. So I can apply this result for 6. 6 divide p square, so 6 will divide p. This implies p is multiple of 6. So we can put p is equal to 6m here. Let p is equal to 6m. Putting this value of p is equal to 6m in question number 1, we have 6m square is equal to 18q square. 36m square equal to 18q square. This will become 2m square is equal to q square. This shows that q square is a multiple of 2. That is 2 divide q square implies 2 divide q. From this, p is a multiple of 6m and q is a multiple of 2. This shows that the GCD of this shows that p is a multiple of 6 mean it is a multiple of 6 and it is a multiple of 2. Now the GCD of 2 and 6 is 2. It means 2 is a common factor between p and q. So GCD of PQ is 2, which is contradiction to our assumption that both have a common factor 1. That leads to the contradiction, hence our assumption is wrong. So square root 18 is an irrational number. I hope today's lecture is helpful for you, and now you are in position that you can prove the irrationality of any number. Thanks for watching Inshallah, in the next lecture, we will discuss another important topic from your book, Principle of Mathematical Analysis. Take care. Allah Hafiz.